at the Yale University until 1996. He was a professor at the Instituto de Neuroscienza, University of Valparaiso since 1996, and a researcher at the Centro Interdisciplinario de Neuroscienza de Valparaiso since 1999. His work extends to the Instituto de Sistemas Complex de Valparaiso. I'm sorry, I don't say a word of Spanish, so I do my best, since 2005. And he was a visiting professor and associate researcher with the Cortex Inria UHP team in France from 2008 to 2010. So his research interests include sensory biology of the visual system, focusing on the physiology of the retina using multi-electrode arrays and patch clamp techniques. He also investigates neurodegenerative processes in rodent models of Alzheimer's disease, looking at behavior and synaptic plasticity. Moreover, his work encompasses computational neurosciences and neuronal coding in the retina. He's interested in the neurobiology of learning and memory, employing behavioral, biochemical, and synaptic plasticity, approaches to address neurodegeneration during ages. His lab uses transgenic and natural models to study aging in Alzheimer's disease. Sorry, and I leave the floor to Adrian.
Uh, okay. Thank you very much for the introduction, and I'm very honored to be here. I mean, just after the lunch. I mean, and what I would like to do this afternoon in this presentation is, I would try. Don't show like most scientific data, but more my own perspective or an experience with a collaboration with a group in France that is from Inria, and how this has a lot of challenges, because that's make when you adapt to a new groups, new subjects, or you try to collaborate, does also need flexibility, plasticity, and that your own lab also change a little bit perspective. So this is the story of my experience with the a group in France in the area. So I would like just to mention my own field of work in science, but also how I has been moved also to more numerical um, data science in the near present. So this is also, so I would like to start with that. My field in general is neurobiology. I just changed in reality is neuroscience, but was not matching very well neuroscience and computational neuroscience. I put neurobiology. That is quite the old name for this link between neuro, brain, and biology. No? And how the idea is just to, I have a start. I want to use this maybe with this intersection between sensory biology, brain science, and today what is called artificial intelligence, because it's a very fast and evolving field. I mean, before we were talking about models and computational neuroscience or biological models, but today everyone is talking about artificial intelligence. I mean, in general, that has been for the last, I say, years, no more maybe the two, that neuroscience is completely, today with this name associated. So I would like also to take this in care and try also to identify some of the main challenges that we have been involved in the last years. That one is how we integrate, artificial intelligence in neuroscience, with neuroscience, and that's make, first of all, that the brain is a very complex system. I mean, that's something that everyone knows since, many hundreds of years, quietly. And still a complex system in the sense that it's a very tiny organ, 1.5 kilogram with 10 to 10 neuron and more synapses. So it's something that in this small space, this small volume, everything that the brain can do is something that we haven't yet, been able to replicate. Same if we have all of these computers today associated with artificial intelligence. So this is still a main challenge that has not been moved, but had not been resolved, but already pose some problematics. One is the way that we understand sensory processing, that we need this model for just for the design, how the design of sensory system has been evolved in nature. It's something that is still a challenge. I want to show something in the next slides. Also, consciousness and cognition is one of the big, point also that artificial intelligence also try to simulate it, and that's start what I see like the frontier for the ethics, the ethics and privacy concern that today we are confronted on. That is how, we protect our own mind from being taken, their contents, and use it for business, for publicity, just to try to modeling, what you're going to be doing in the future. And that is something has been very present in the last year also with this like interface that is, artificial intelligence with all of his method, and that has permeated the biology too. Chile is one of the examples of that we have changed the constitution. I mean, the past one, just try to protect our own mind from being used or read for artificial machines. And also, that's apply this new, I mean, agents that start to work it together. That's neuroscience also and artificial intelligence. That is an interdisciplinary collaboration, and that's make that the methodology that we have here just before. I mean, in an artificial intelligence has their own paradigm about what is true, how we just converge. I mean, what is the critical aspect of reduction of error? I mean, there's are a lot of, I mean, hypotheses also used in the, for the side of the computational in general, informatics, and now moving to what is the biology of the brain. So this is something that is we are facing that maybe we are not talking about the similar language, but we try to just put data together and just discuss about their projection. And also the scalability of the model in artificial intelligence also is something that is one big challenges, how we move from little model to the big models, I mean, that take a lot of data. That is something that we are discussing when we face also in the side of neuroscience that we started many, many years ago just taking one cell at a time, and all of our concept for in the brain was taken from single cell response. This is the classical, I mean, years 60s where people were doing that way with patch clamp or intracellular recording. I mean, taking one cell at a time, just try to predict what was the work of the whole brain. Now we face very nicely methodology where we can just grab thousands of neurons in the same time. So this is something population coding now that we are taking account. So we have moving to the big scalability that also face some problem also for artificial intelligence. And I'm gonna move from here a little bit, and this is something where I has begin many years ago when I returned to Chile from United States and before I was in France, that I was very interested myself, I mean, in the biological root of our sensory capabilities. That means for me was at that time that how our sensory system, they are coupled to their own, I mean, space where they live, where they need, I mean, to just to take food, reproduction, and so on. I mean, the life or the fighting for existence. I mean, just to be there more time than sometimes than the others. So this history make that the very good understanding about what is the light, you know, in natural space, how this impact, I mean, their own design for a species that live in this place. So I started to work in this area because it was a little bit no more in Chile about the knowledge about the species that were living in the South America, essentially in Chile, about their own design, their own visual system, how they are, I mean, they are coupled, or if you know where they live, maybe you can predict what is their sensory life. So we start working with a couple of ecologists in Chile, just trying collecting animals that are an example of rodents that from one family that is Octodontidae, that is a family of rodents that live in Chile, and we were very curious about their. Let's see here. This is a retina. This is a piece of the retina. This is the layer that is in back of the eye that is in charge of the capture photon and transduce this to the biological signal that the brain reads. And this is just antibodies against, I mean, that mark cones and conta are sensitive to the ultraviolet in this case, and other that are sensitive to the greens place in the, I mean, in the green absorption position. I mean, and this is something that all of these are dichromatic animal, but one is an diurnal one that has mostly of close to 30% of their own photoreceptor. I mean, the sensor that capture light are cones, and the fellows, I mean, this is the cousin that are from the same family, but this one is a nocturnal one, and only the 2% of their photoreceptor are cone. That means that they're very sensitive. More you have cone, more you are sensitive to light. I mean, you can just develop your life during a lot of light. I mean, they are diurnal species, and these are nocturnal, and this also is another one. Is Vigesi also is a nocturnal one. As in, is another one that I'm not showing here that is called Spalacusiano, it's called the Kururu, that is completely fossorial. That means that live underground and just go out some time in the day, but just like not seeing nothing, just taking sun. And his own visual system is, I mean, it's very close to a diurnal one, and that has been, we were speculating in a couple of papers that actually the natural pressure to be underground is not enough to develop a visual system that actually match light that is there. I mean, nothing light because it's just underground. So this is something that sometimes you need to take care also when you are studying evolutionary development of the visual sensory system, that sometimes your activity is important also to determine your own design for that. So this is something that we have shown. I don't show it here. And then I start to moving the following year to something a more general question about, okay, I'm trying to, this is, I mentioned here also my colleague here, Maria Jose, that has been one that we have been collaborating a lot of since many years, that actually when you start to having this like more natural design, you start also asking another question, Armand. What happens when you go to the lab and you start to working with physiology, doing patch clamp, doing biochemistry, and then in the future we were doing like multi-electrode. I want to show that recording with thousands of cells. You start thinking, and that's very good for the collaboration, in devices. I mean, how we can take this result just to translate the knowledge that comes from design, the natural design, into the lab with all of the methodology that correspond to a lab, and then try to make design for, say, an artificial system for people that has impaired their visual system. So this concept was developing, and this is something that also came after with the collaboration with the Inria teams. And essentially just some brief, I mean, account about what is exactly the visual system is doing. We are working with what we call the retina. This just this layer that is in the back of the eye that is very have an structure very, I mean, very similar in all of the vertebrates, that it actually are for receptors. Then this is where the visual pigments are. This is all of the I mean, biochemistry cascade. One photon arrive here, just work at the level of the ion channel. It's called, there are proteins, and these proteins, when they are open, like a channel, ions just come in, and then other come out, and that create what is called a photocurrent, and this photocurrent just control what is the liberation of a neurotransmitter. ¿Ah? Aquí, ya, ok. O me pasa el otro, ¿sí? ¿Ya? Para no estar así. Yeah, okay, that's better for me. And it's okay there. And this is, I mean, this is a retina that has been isolated from the eye. It's really a layer that is very nicely to see. I mean, when you working in this preparation. And here is just a high, I mean, resolution for receptors. These are like 20 to 30 micron long, and then sometimes between 1 to 10 micron or diameter. They are very tiny sensor with thousands of the visual pigment that are in shadow just to capture light when light arrives. And then the cascade come down here at the level of the synapse. This is for receptor side. This is a bipolar cell. Then it's another layer of synapses, and these are ganglion cells that they are a family of different type of the ganglion cell here, and also a variety of also of bipolar cells and a Macquarie cell and horizontal cell here that are more like connecting laterally the input from receptor to bipolar. So this is like a natural design that has been created to capture light, but not only to capture light, but also to treat light in the like a signal, in the sense that there are in human 150 million of photoreceptor and 1.5 million of ganglion cells. That means you have a convergence here that is completely, amazing. In between, you have a lot of local and less local, network. So the output of your retina gave you a big possibility, and I want to show this after. I show just this before, that this is our lab. One of the setup in the lab that is we're using micro electrode here. This is very tiny, 1 to 2 millimeters square with 256 electrodes, and now we have 4,000 electrodes. And all of these small windows with a spike here are the recording from cells. The hundreds of cells from a retina. This is also the activity that is we call a spike. That means it's the action potential that comes from individual ganglion cells. And then we transform these signals after doing what we call spike sorting in a lot of temporal series of time here. This is time, and here is the number, is just an example of recording 20 cells here, and here is time, and each bar that is here is the time where one action potential occur. This is there. So this is what people that use numbers like, because it's a lot of number. When you record it for 1 hour, one ganglion cell can have 20,000 spike. It's a lot of. So then the story start with our collaboration. And now this is also from a paper where Maria Jose was one of the authors here. And this essentially is we use like what we call white noise just to create to record what we call the receptive field. It means the area where a sensor, one ganglion cell is, actively, is active here. That means all of the photons that arrive in this area, one particular ganglion cell respond. That is called a receptive field. And also one particular also of the retina is that it has, from the beginning in this bipolar cell, have two types of receptors that are protein that are sensitive to glutamate. And with the glutamate, one type of this bipolar cell depolarized, and the other set of bipolar cell hyperpolarized. That means you have like this switch between light, that when the light turns on is one set of neurons that are active, and when the light is off is another set of cells that are active. That means you have this path here that has already an identity from the beginning. They're on, and that is the way that the retina responds also to the contrast. And the network, when it's organized, that also make a lot of possibility to the computation for movement, for contrast, for orientation, and all of these properties that are created by the network. They are not a single cell that is able to just compute movement in itself, but it's the network that is in charge. And essentially, this is a cartoon, but it's original data from another lab in the United States where they have simulated each time that you have a dot here that is red. That means it's the time that an spike, an action potential arrives. That means the idea is that when this turn on here is on color is red, this is one signal that goes to the brain. This is the output of your retina when you are looking here in this present moment. Your retina is sending spikes to your brain, not a picture at all, but just a pattern of response. And this is what the brain used to learn about what is in the other side. And so this is a big problem that people has been trying to solve in the point of view of biology, how we generate this pattern of response, and also is any sense in terms of the entropy, the mutual information, the population coding, etc. This is the way that we have started working with the colleagues in France. Just we doing the biology, and then they're doing the models. No, so this is a picture that I just create artificially. this purpose. And one way also to see that is that when we have just an idea about the diversity of the way that the retina work is also when you use this small light on, off, etc. This is 40 millisecond on and 40 millisecond off. You create this, there are different cells, I mean ganglion cells, that create, when you repeat the stimuli, you create different pattern of responses. It means that one cells in your eye, I mean, is just sending a spike signal to your brain in that way. I mean, just a lot of in the beginning, then a little bit, no more, and this another one that has a little bit more response. This one has a bigger response. This another, and etc. I mean, you have, I mean, so many ways to to send this pattern of response to the brain that the brain need to learn about this pattern to make sense of the work. I mean, this is the idea of the big loop that we are always trying to resolve. In the last year, we are like working also with a group in France, with Bruno Cessac and others, to try to do clustering about many cells. This is an example of more than 7,000 ganglion cells that we were recording from this model here, this rodent that is Octodon deus, and we just using clustering in the way that the cell respond in time to a particular stimuli, you can classify these cells in families, and these families can be on, off, fast one, in the frequency, in time, short time. They can be also sustained. I mean, just responding during the whole time of the stimuli or just in the beginning. All of this make, the properties of these cells. I mean, this is the idea. And this also we have another example here is just using only the on cells in the retina. This is the stimuli that we are using just to make these cells talk. And here are the pattern. These are the feature calculated from population of cell. And this is working very well. And actually, with this kind of the experiment today, we can do a lot of modeling about how the retina is responding to natural stimuli, and also how the retina is also communicating during health or disease with the brain. So this is another aspect in the lab that we are collaborating. This is for the off. I want to just jump. And this is on many papers that we have been producing, many of them, some of them, in collaboration with the Inria or our colleagues in France. Has been a very nice, collaboration. And let me now to switch to how we get together. And I have been very lucky to work with the Inria colleague, with Fred Alexander, that was at the time, 2008. I know him and his group a little bit before, but I spent 2 years in France, 2008, 2010. And he was in Nancy, and then he moved to Bordeaux, and then to Sofia, where it was another group there with Thierry Vieville and Bruno Cessac. Maria Jose was there too, a little bit before. So today I just moving, when I just go to France, between Bordeaux and Sofia, and it has been a very nice history of the long-term collaboration. That I say, I just start with a sabbatic year. That is very important to have the time when you are trying to collaborate with groups in other countries, just to have the time to go there. To visit them, to see what they are doing. Just to have a coffee or wine or whatever you want, what for that. And that is very important. The other thing is very important, has been also a key moment, for exchange, is that the complementarities between groups, biology, physics, mathematics, computer science. All of these make things, go, very nicely in time, because the problem can be afford and complement from different point of view. And from the beginning was also the group in France just applied for an associate team. The first one I was involved with other researching in Chile, but was very centered in Valparaiso, was the Cortina, that was in charge, was Frederic Alexander in France, and we since that time, uh, we were working on was a very nice grant that was in the past that was when I Einer and was CONICET at the time that allow you to do research, not only just the trip, just make an exchange and go there and they come here, but this grant from the Einer was very important for us because we just put science in the bench. I mean, we were able to do experiment together. Before, I mean, with the other project was not possible, was only exchange. And the problem that is very good for mathematician or physics, when you have this like echoes on other grants, but for biology, it's not enough. We cannot plan in any experiment if we are not having this type of the project. We don't have this anymore, unfortunately, but I hope in the future. And with chaos, the main concept that we were trying to develop was something that I maybe mentioned before, that is the diversity of these ganglion cells that are the cells that are going to the brain, and they are not one type, but there are many types. I mean, at least 20, 30 types of different ganglion cells that you can just think about. I mean, what happens if I have like 20 or 30 cameras in front of me, and all of these converge and goes to the brain, and the brain try to identify what is there, what is in the other side, just to make a plan about how I move, is my perception, how just I compute the color, saturation, I mean, things like that. That's the way that the brain, I mean, is talking. I mean, with the eyes. It's not one output, it's not an image. There are different patterns, how the one that I showed you before. This is dot that move a lot of, I mean, in time. This is the signal that the brain received. So this was put in the center of this project with the Inria group, I mean, in France, that gave it 3 years of work together. And then, I mean, the last year also, I was also involved in this other associate team, that's Magna team, that now is in for a new term. I mean, we are applying just to continue this one. And also, this has been also very nicely done, I mean, in collaboration with a group of Bruno Cessac, another researcher in France. And I just have put here, yesterday I was trying to remember the grants that we were collaborating with the Inria group. And this has been from 30, I mean, from 10, a little bit more than 10 years ago. And there are many. We started when I was there, with a project that was called Neuroinformatics from the CNRS. It was the first grant that we got together. I was in France, and we just applied the same year, and we got one for transduction and perception. And since that time, every year, mostly, we have having grants, with the Inria group. And just with the chain where students were working there, then we got this Millennium, this network, and I also, I mean, thank you also to Maria Jose is here, is everywhere Maria Jose is here. We have collaborating all of the time. We are collaborating with people, I mean, researchers in France. So this has been a very long history of, I mean, collaboration. And also this is a paper where with Bruno Cessac, this is with Fred Alexander here, and all of these are in retina. And that is also, this is nice because if I have changed myself from biology, from the ecological point of view, just making sense of the sensory system in the wild, I mean, how they are the design, then I have moved to the more like computational neuroscience, and also bringing more data from multi-electrode, I mean, more population neuroscience. But Bruno is the one who has changed completely his topic of research. Now he's only working in retina, and since I know him before, was working in another subject, but not in retina. So this has been a mutual change. I mean, everyone has been worked to a place where both labs now work together. I mean, I just mentioned this because it has been very important for that everyone need to move a little bit to the center of something if you want to collaborate. Yeah, and also one very important also recommendation that I also always have is that we create a common school. And that started in 2010, just after I finished this 2 year of sabbatic in France. We started with a school. We're in a school that was the first school of Latin America, neuroscience, computational neuroscience. And since that time, every 2 years, sometimes every one, we have this school where always has been one from France. I mean, this has been permanently. This has been a very nice story. There are many, many students that has been uh, go to this school for all of Latin America and also for Europe. And then I also another way to collaborate, and I realized also yesterday that I has been involved in many theses. I mean, like an external reviewers for the thesis done in France. I mean, this also make a lot of work together. I mean, it's a little bit more work, but it's very nice to see how the students from France also are working in this subject. All are from retina. You know? And just to finish a little bit about what is maybe important also is that in your own labs or where you are working is to try to put bridges, and bridge from your models, different models, and uh, kind of the formalization about computational neuroscience. In our case, how the computational neuroscience can afford, I mean, different part of the I mean, in this case, is the nervous system, the brain, how the brain works. But you need to create paths. I mean, here is one sensory transduction and encoding. This is one way to study entropy. In one way, this is a neural network. Also, when you are working in developmental neuroscience, also you can associate this with computational neuroscience. So the idea is always to have something that make the link. Molecular transaction, stochastic model of calcium channel, for example, is something that has been a collaboration in our interdisciplinary neuroscience center in Valparaiso. But in the center, always you can put something that make sense to the other side of the lab. I mean, the other lab in the other side. So this is something that you can do actively, just making bridges. You know. This is the same example. I mean, about synapses, brain in general, and also going to computational model. And we have learned in this morning. I mean, some of the big challenges that this also has. I mean, and just to finish, just make sense. I mean, thanks to students that has spent time in the lab, essentially in Sofia, and also all of the grant, and just name some of the main collaborators in this last 10 years, or a little bit more of collaboration with France and Chile. And this Bruno Sack, Thierry, Frédéric, and Maria Jose here in Chile. And that's it. Thank you very much for listening.
So, any question?
Hi. So thank you very much for your talk. And regarding the eye, the retina, how to say, sensors that you were discussing. So is it among your goals to develop functional eye prosthesis? And how far is the state of the art from this goal? If someone is working on it.
Yeah, there are many. I mean, we start with this is essentially something that has been thinking a lot of. I mean, in the Sofia groups, in terms of in collaboration also with the Institut de la Vision in Paris, in the sense that you need to have something that in the beginning where like the idea is that if you know more about the biology, the physiology of the retina, then it could be much easier just to create something that you can put in their place, and has been a lot of try doing that. And the last test that I have is in my knowledge. I mean, is they're quite not. I mean, they're very good from the point of view you are blind, and you just have like an artificial device just put in the back of your eye, and this make sense between light and some signal that are sent to your brain, and the brain sees things, you know. But the resolution is always not so good. The point of view of our resolution, I don't see it for the people that are blind. Is fantastic, yeah, right? One of the best solution today essentially doesn't come from that place. It's not for artificial device. It's more like from biology in the sense that you can now just create, I mean, artificial sensor and put it back in the eye directly using biology to solve biology. So this is something that has been changed a little bit. But what is really good on that, that you can create something that help a lot of your vision, just to enhance your vision, like this portable device, you know, that you can see a little bit more, you change a little bit more in the region of the spectrum that you are not aware of, like ultraviolet or infrared, just try to make the conversion. That can help a lot. And I think this is something that is in the group in Inria, always they are thinking on that. I mean, so the field has been moving a little bit, but to enhance your sensory systems in general, in particular vision, is something that is there, but it's a little bit more like an external device than more an internal device. You know, this is something that I can say.
No more question? Okay, so it's time to thank Adrian again. So now we move on to three talks. So first, Nicolas Hara. So Nicolas is from the Department of Electronics of the Universidad Tecnica Federico Santa Maria. And so he got his BSc in degree in telematics engineering and his master degree in telematics engineering at the University Tecnica Federico Santa Maria in Chile in 2010. He completed his PhD in a double graduation with the University of Rennes 1 in France and UTFSM in 2017 and 2018. Respectively. Dr. Hara is currently an assistant professor at the Department of Electronics at UTSM Chile, and his current research focuses on optical network planning, networks performability, simulation techniques, and machine learning-based telecommunication system. So I leave you.
Okay, thank you very much. I first want to thanks for the invitation, Nayat, Luis, for taking me here, for inviting me here to be part of this great scientific journey. Okay, well, tons of machine learning we have seen today, right? And I trust that on Monday and Tuesday too. So let's talk about something else. But don't you worry, machine learning is there too at the end. Okay, so we all know, we all trust that internet is among us, and it's a resource that we are going to have all the time, yeah, from now to the future, yeah. But we believe that this tool, it would be forever, and it's trustable, and it can offer to us all the things that we want, all the data that we want, all the information we can communicate from one place to another, and it would be great. It would work, and it would be secure, and it would be effective, right? Yet, there's some problems. Yeah, we have a very interesting age in which internet has so many demands of data, so many demands of bandwidth, that there's a lot of challenge to face current needs, current demands for the internet infrastructure. So I am going to talk about the next gen optical networks, which is the basis of all internet communications, and how should we plan their smart architectures for it to work accordingly. So we all know about these demands. We all know about all of these technologies. We all use it more or the other, right? Yet, since they grow so so significantly, that it provides a very it stress our infrastructure. So in the end, we have there's a bandwidth demand compound annual growth rate around 40 to 30%. Yeah, so it's like similar to the Moore law. It doubles every 2 years, more or less. So that's very important. That's very stressful for the internet traffic. So we can see, for example, in here, this is a test. This is made by telegeography that shows that how the compound annual growth rate grows from 2018 to 2022, and it's around to 30-40%, no matter the region. You can see Africa, Asia, Europe, all of them are growing similarly. And even on COVID, we foresee, well, the engineers, the researchers foresee that there will be like 28%, but the observed was 47% in increase of bandwidth demand. In Chile, they tried to also, in 2017, Infraestructura Pública tried to make a statement, and in 2017 they test that they have in Chile, we have 2 terabytes per second in international and national bit rate, and we should expect in 2037, 20 years from that study, there will be 81 terabytes per second, right? So it seems like there's a lot of growing. But there's a lot, but those architecture, those deployed infrastructure has to be able to support all of these demands. All of these demands are supported by internet. This is a very interesting map, a submarine cable map, that shows basically how the world is connected through cables, through optical fiber cables. We can see that, well, it's not very clear from this point of view, but you can see there's a lot of lines through all the continents, even in the continents. It's all based on optical networks. The transport layer that we talk about in telecommunications and telecommunication networks, in telecommunication systems, the transport is supported basically by optical fiber. So the optical fiber should be able to support all these demands, all these internet demands that we all need. Yet there's a problem. Researchers a decade ago foresaw the transmission capacity limit of telecommunication systems might be reached in the near future. What are we talking about? First of all, let's go to the basics. In information theory, Shannon, maybe you have heard of him, proposed a mathematical theory of communications, which he called the channel's capacity, which he calculated, or he published, that any communication channel can be characterized by 2 factors, bandwidth and the signal noise. Yeah, we know it now as the channel's limit, which shows us that theoretically there's a maximum limit rate to transmit over any possible or any channel. Yeah, over any communication channel, with a specific bandwidth in the presence of channel noise. Yeah. So let's see a study in optical networks. this study shows that many improvements have been done on the fiber optical communications. Yet, around the 2020, they foresaw, this is a test, this is a research, from 2015, that they saw that in 2020 we would achieve what is called a capacity crunch. A capacity crunch, it means that there's a limit, a theoretical limit, that our fiber optics in the current way to transmit the information would not be able to even surpass that. We cannot transmit more bit rate on the optical fibers. So what's the answer for that? Well, let's see some other information that is interesting. So let's say, how much capacity do we need over the Atlantic? We're talking about the most, with the higher traffic pathway that we have from America to Europe, basically. The amount of new cables required, I'm sorry, this is the capacity requirement in terabits per second. In blue, barely seen, is the current infrastructure deployed, the current fiber cables installed. The yellow one is the planned one, because, well, as you may know, it's very costly. It's very expensive to install any fiber cables and all the equipment demand required. And the red ones are the ones that we demand if we follow all the growth on bandwidth demand that we have been having on these last 20 years. So you see, in 2035, we need a lot more than the ones even planned. Even more, optical fiber cables has a lifespan. The first one, they were installed on the 90s, at the beginning of the 90s. They have a minimum lifespan of 25 years. So now, of course, they will start to die. They will start not working. They will start to fail. So even considering that, you can see that in the Atlantic, in 2023, we have like 12 or 13 optical fiber cables, but they will be starting to be diminished, since they will not work anymore. Yeah? Of course, this is all probabilities. Yeah? Nobody says that in 25 years they're going to die, but they will. They would. So this is how many cables we should need in around 15 years ago. In around 15 years. In 2035, we'll need 40 new cables only in the Pacific, only in the Atlantic, extra from the ones that we have now and the ones that we have planned. So that's a very interesting. And in the Pacific, it happens the same thing. We need 20 more. Yeah. So we have a problem. Let's see some graphics. This is the amount of cable, submarine cables. In 2018, if we add all the planned cables we have, it's considered to be installed. And if we erase all the ones that should die this decade, we have all of these, only these ones. So this is quite interesting, because this is not just about the capacity of the fibers itself should be used in a more efficient way. It's also that they may die in the near future. So it seems like it's very chaotic. It seems that it's an actual threat. So what should we do? Well, first choice, of course, you should spend more in fiber cables. Let's install more, of course, just like that. But of course, it's too expensive. Yeah. So it must be done, of course, but it's way too expensive. So let's see some other choices. Well, we could build tons of data centers. Let's build data centers close to us. So we won't be needing so much the optical fiber for tons of data that data centers usually need. So we use this fog or edge computing kind of solutions, so we won't need the optical fibers that much. But yet, of course, it's also costly. So we need something else. All right? So if we want to face this capacity crunch, there's at least, well, there's some solutions, some ways to face it. On the one hand, we have we could multiply the resources. It's not just about installing more cables, but we should multiply the resources in a more efficient way. So we may install something else, but this one, it should be more efficient, larger bandwidth, or it would be, I don't know, multiplied by more than 2, for example, the resources needed. On the other hand, we can use some efficient management. Optical fibers, we are handling light. That's an issue in engineering, because it's a very hard resource to manage. So in general, it has been done in a very static, in a very simple way, in a very straightforward way. But we can do it much better if we try to manage those resources in a much better way. First of all, optical networks, currently, they work like that. We have all internet service providers. They have been operating with the ITU standard, right? 50 gigahertz per wavelength. We have WDM, this is multiplexing in wavelengths, because we are working in optical networks, in optical communications. So we have 50 gigahertz of spectrum for each wavelength. Yeah, those are fixed, cannot be changed, cannot be moved. So it brings some difficulties in the management, right? Because now we can need 1 terabit per second as a transmission, or 400 gigabit per second of a transmission for a connection, and they won't fit on these 50 gigahertz. So it's difficult to manage. So one of the possible ways to try to solve, to try to obtain a more efficient way to try this, is to change from the static operation of optical communications. It means that all the resources are permanently installed for the users, no matter if they use it only at 20 or only at 30% of the time. So we can have a dynamic operation based on demands, basically. Whenever someone wants to try, whenever someone wants to transmit, they will be given the resources, and then when the transmission finishes, it could be released for the users, for other users to be able to use it. Yeah, but we are using some. There's some problems in blocking probability, because since all the dynamic solutions, all the dynamic resources allocations demands that there would be a possible way that they will not be able. The capacity would be used for everyone, and someone else wants to transmit, and they can. So with these architectures, with these solutions, and in cooperation with the Inria Chile, in 2013 to 2017, we made a software allowing us to plan this kind of solutions, or these kind of architectures, for there to use the resources in a more efficient way. We are talking about routing, fault tolerance, dimensioning of the resources that needed over these optical networks. Lately, we can do more efficient solutions. This architecture is called the elastic optical networks. Instead of using this 50 gigahertz fixed grid that we have in the spectrum on the optical communications, we can make it on demand, depending on the user, depending on how much bandwidth the users need. So it can be used in a much better way. So the problem commonly found in these architectures, as I said before, we can solve about the routing, we can solve about the spectrum allocations, about the format modulations, dimensioning, and fault tolerance are the main problems that we should have, since all this efficiency brings a lot of problems on the solutions, on the architectures. And also about when we try to multiplex, we can use all the several multiplexing techniques. Yeah, we know that there's a lot of multiplexing on polarization, frequency, time, quadrature, but we can use space. So two possible solutions that we have been working on in the researchers in optical networks have been working. One of them is the spatial division multiplexing, changes the fiber with multicore or multimode transmissions. So there's a fiber. You can see different possible solutions. The optical fiber can have different cores where the optical transmission can be sent. So multiplying the resources. Yet there's a problem because we have some physical impairments that we have to handle, known as the crosstalk. And also the ultra-wide band optical networks is to use different spectrum bands available on the, of course, in the optical fibers, but not used because they have complex physical impairments. So we may use it, but we know that some of them has worse performance. So yet we can transmit solutions, we can transmit communications for a shorter distance in a bad band and in a good band, in the C band, that is the one we're using now. We can transmit for long reach communications. All of them needs to be solved, and it needs to be solved as a network planning solution. So some of them we can use optimization techniques, which are very common, but commonly known as an NP-complete solutions in some NP-complete problems. Some ad hoc and meta-heuristic protocols can be made. We have been working on that, on several possible solutions. And the most important one now is to apply deep reinforcement learning techniques. So some of machine learning. Yeah. So in this we are trying to use an agent who learns from an environment that simulates the optical communications in all of these architectures. So this to find in the end some promising solutions in designing new routing strategies or implement dynamic resource allocation schemes to accommodate the real-time changes in the network architecture. So we made a framework or a toolkit available for everyone if you want to use it, which uses several agents available on the literature to train this agent and to be applied on optical communications. So we call this Dream-on-Gym, so it's deep reinforcement learning framework for optical networks. You can download it right there. And it's a very interesting solution that we have now. Of course, there's a lot to be done, and some challenges is to face optical networks in a smart way. Optical networks must be reconfigurable. We need to tune all the parameters. That's on the device's point of view. But of course, but also we need to be orchestrable or programmable. We need to change all the possible solutions so we can have some control panel, so more interesting or more adaptable reconfigurations. And in the end, we needed to be autonomous, to be able to reconstruct, to reconfigure, depending on how the network is working or how the traffic is working, or how everything is working. Using AI or not, we need protocols, we need information, we need solutions from this point of view. Yeah. So all of this has been done, of course, in collaboration. Some of them with Inria. I started as a project engineer in Inria, Chile. Lately, I did my PhD in Inria in France. So we have some Stick and Sue, the ECHOS, Fondesit projects, and also collaboration with the IRO research team. It's a Chilean optical network research team, also working in these problems with several universities, as you can see. So, of course, we are still focusing on these problems and trying to solve many, many more. So that's it. Thank you very much for your attention.
Thank you, Nicolas. Time for question.
Hi. So thank you very much for your presentation. And my question is regarding the graph where you presented the projection for 2035 and the problem that we're going to need much more bits, right? So is in this projection considered the satellite internet such as Starlink? And how, if it's not, how would this change the the projection here?
Yeah, the satellite communication works for a very low bandwidth in comparison with optical networks. Optical networks, they can transmit tons of bits per second, terabits per second. And the satellite may work for the access network. I mean, in rural, for example, places, on the country field, it would be interesting because they can have internet on their homes and using these satellite transmissions. The problem that satellite transmissions had also is about the delay. Yeah, because you need to send all this information to space, then to back to the Earth. So there's a lot of problems with the delay that you can have. So it works, of course. It's interesting and it's a good solution for those kind of places or in overseas, for example, and that kind of solutions. But with the main part, you need optical networks. So so it's just a little bit of bandwidth that you may try to use with satellite communication instead of optical networks.
Thank you. Oh, very quick question.
Hi. I've got kind of two questions. The first is about context. I was not very acquainted with the problem you presented, but I was wondering, like, how does this work on the market side of things? Like, who owns these cables? Who maintains them? Who is deciding what projects are going to be carried on in order to have more cables? Because they probably have their own motivations and will want to know different things. And maybe one could wonder the market would solve the problem in some capacity, like it's going to be, I guess, more expensive to transmit certain information, and maybe that will do something. And on the other hand, I'm wondering if the tuning solution you propose has a trade-off with reliability or with robustness, because you're saying like we are going to squish, I think, in a way, the frequencies. Is that going to shift according to demand? Can that have like a that have consequences for the data being transmitted?
All right, a lot of questions. Let's start with the first one. And there's companies, international companies that install these optical cables. We are not installing, well, of course, there's the ISP, the Internet Service Providers, who install the fiber over the countries. But outside, when we are talking about submarine cables, there are international companies who do that. Yeah? And they foresee, they use some enterprises or foundations that they see these needs. For example, Telegeography, Siena, or another companies that they install or they check how internet is working. Okay, even some content enterprise, they are installing fiber. Actually, Google, Facebook, or Meta, they are installing fiber cables for themselves. I mean, from to Chile, we have a Google cable connected here in Valparaiso directly to California, yeah, just for Google and Google traffic. So it's actually it's very interesting. It's growing this content enterprises installment of fiber cables. Yeah, and instead of on the reliability point of view, part of the planning strategies that we should face is to consider all the possible fault tolerance, is to include some fault tolerance capability. And this is related to actually the reliability. The networks has to be capable to be to accept or to be available even on the cases of some of their cables are shut down or fail. And the decisions on the resources, they need to have protocols to change or to be adapted instead whenever these situations happen. So it's part of the planning strategies to consider all fault tolerance capabilities.
Okay, thank you very much. We have to stop here. Thank you again,
Okay,
Nicolas.
thank you.
Now we have Fabienne Riquelme from University of Valparaiso. So Fabienne is a computer engineer from the University of Concepción, Chile. He earned his PhD in computing at the University Politécnica de Catalunya in Barcelona. He completed a postdoc at the IT Innovation Center for Social Application at the University of Santiago de Chile. And he is currently an academic and researcher at the University of Valparaiso, where he works as a research and innovation coordinator of the Faculty of Engineering. Alternate director of the Doctorate in Applied Computer Engineering and alternate director of the Center for Interdisciplinary Studies in Social Theory and Subjectivity. So his main area of interest is our social networks analysis, social computing, cooperative game theory, and multimodal analytics. I leave you the floor.
Thank you very much. Thank you all for being here, and thanks for the invitation and organization. Well, I will talk about my main research project that started in October of this year. It will last 3 years, and it's about my main research topic, which is social networks from a computational point of view. So I will present the main results in a brief way without any technical issues. This project, the main aim of this project was to relate two of the main problems in social network analysis, which are the centrality problem and the influence spread problem. First of all, social networks, I understand social networks as any environment, any scenario where we have agents, actors related between them. Okay, so social network is not just a social network platform like Twitter, Facebook, TikTok, etc. But also it can be a meeting, also an informal meeting, and some political issue, a congress, and so on. Any that can be represented as a graph, I consider it a social network. So I will start explaining a little bit what is centrality. Centrality measure is just a measure, a metric that represents the relevance of the different actors in a network. So if we have a network over on the left, okay, so a centrality measure is like an algorithm, a mathematical formula, a black box, okay, that allows to give more information about this network. So it represents in some way a statistical, it's a descriptive measure of the related data, okay? So in this picture, the blue nodes are considered more relevant than the red ones who are in the periphery, okay? So it's a quantitative and relative evaluation within the network structure. That means that the centrality of any actor is given not by itself, but also by its neighborhood and the structure of the graph. So there is a lot of centrality measures. If, for instance, the principal one is the degree. It was defined in the 50s, okay, before the computers. It represents the number of neighbors I have, okay? The direct networks I have. So for instance, here the nodes C and E has a degree equals 3, so both actors are the most relevant of this network in this, under this criteria, and the peripheral, the A, B, F, and G are the less important because only has a degree equals 1. But if we consider other kind of centrality measure, for instance, the distance between the actors, the node D is more relevant because it's in the same distance than all the, is in the middle of the two partitions of the network, okay? So the closeness measure is under the closeness measure, node D is more relevant than C and E. As I said, there is a lot, hundreds of centrality measures. Here we have an example of the same network, but they illustrate different centrality measures. So we can see that any measure rank the actors in a different way. The important thing about the centrality measure is that a new centrality measure must not do the same that other, okay? Because if that's the case, then one of them is irrelevant, it's duplicated. So they must have a different correlation, not to be too much correlated between them. Also, the standard deviation around the different actors must be high, because it is not useful to have a network with the same color, okay? We need to understand what are the nodes more important according to one measure. And the last thing that is important is the computational performance. We need that the centrality measure be with a low computational complexity, be polynomial in terms of the number of nodes, in order to compute the centrality for all the nodes in the network. We can think in a small network with just, I don't know, 10 nodes, but in this example we have a network with 10,000 of nodes. So it's important that the centrality measure be efficient, okay? The other concept is the influence spread. We can understand influence spread as an iterative process, a dynamic process, where at the beginning we have only non-influence actors, and we can activate a seed, okay, of red nodes that can be activating other nodes in order to spread the information or the contagion or the fake news on something else, okay? So influence spread is related with viralization process, and it can be useful in communication networks for information propagation, viral marketing, to detect bots and opinion leaders, etc. In contagion networks, collaboration, okay, and also in comparative game theory, collective decision making, etc. It's a very common concept in contagion networks. For instance, there is the SEER models, which are continuous models, very common in this area. But I used to use some discrete models like this one, the linear threshold model. It was defined in the 78, and it was defined as an optimization problem in 2003. So the idea is that we have a weighted and directed graph that represents the social network. Here we have 5 actors, and the edge between one node and the other represents the influence exerted by one node to another. Also, the weight of the edge represents the strength of the influence, and the resistance of each actor to be influenced by others is represented by its level, okay? So this is an iterative process. If we start with one seed that in this example is represented just by one node, but the seeds can be any subset of nodes. So from this seed, we start an iterative process in which, in the second step, we can note that actor C can be influenced by A because it has a resistance of 3 and there is a strength of a weight of 3 pointing to it. So we can influence node C, but node D cannot be influenced already because A only exerts a power of influence equals 2 to it, okay? And it has a resistance 7. But in the second step, we can activate D because now we have together the active nodes point to D with a strength equals 8 that is greater than 7. Okay? And now the process ends because we cannot activate node D nor this one because it has we can only point to it from D and it's not enough the influence pointing to it. Okay? So the process ends and the final influence spread from this seed is all of these 3 nodes of here. Okay? So that's the basics. In our project, we state 2 main hypotheses. The first one was this one. In real social networks, I emphasize the real because they are not. We didn't use mathematical models, but real social networks collected from real data or from some real databases. In real social networks, the most influential actors can be distant, not being directly related to each other. That was the first hypothesis. And to do this, to prove this hypothesis, we first started to defining a new centrality measure that considers the influence spread process. So it relates both concepts. Here we have a graphic that represents some results that we obtained. The picture on the right is the same that the left, but from the top. Okay. So here we have a network with 18,000 of nodes. These are the nodes, and this is the level of neighborhood that I consider at the beginning for each node to be activated as a seed before I start the influence process. Okay, influence spread process. So if we and this one is the total influence spread from my original seed. So if I consider only myself without any neighbor, it is most probably that I cannot be able to influence any other, or just my mother, my father, I don't know, and my best friend. Okay, but not too much. So that is what happened here. I not be able to be more far away from the network. But if we consider more deep levels in my initial seed, I can be convincing and influencing more in the network. Okay, so we obtain this sigmoidal behavior. Okay, in which note that the level 4 is very interesting because it is the main the key point that in which grows the influence spread. Okay, and this result is very interesting also because it is the same that theory says about the 6 degrees of separation. I don't know if you are related with this theory that says that we have 6 degrees of separation. We know that we know that we know something, okay? And we are all connected with all the persons in the world with just 5 edges. Okay, that's the idea. But that theory is for the 60s. Nowadays, with the globalization and the social network platforms, it is being demonstrated that this number is around 4.5. Okay, so that's what we obtained without looking for. Okay, we continue this research by generalizing this centrality measure, and we also consider some variations. What happens if I can only, if I can't count with the 100% of my neighbors? Okay, so we can consider a random value that which says that probably my mother maybe she cannot help me to start some campaign. Okay, so there is some probability that my neighbors doesn't want to help me. Okay, to influence in the network. And also there is some variations around the direction of the relationship. Okay, so we consider the some in degree, out degree, and both directions. So we obtain this generalized centrality measure, and we prove in many social networks, real social networks, with different size and different, okay, and different 5 minutes? Okay, not seconds, okay. So we have different networks and with different density. So we prove a lot of executions, and we do many correlate matrices to find some relationships around the variables. And our main conclusion was that in well-connected networks, it's better to convince first other distance network than the most close one. Okay, so this allowed us to prove our hypothesis. And it's interesting because the well-connected networks are not the most common in real environments. Okay, the most common is to have loosely connected networks, in which case it is a better strategy try to convince first my close neighborhoods and then start the influence spread process. Well, also, our second hypothesis was that to maximize influence spread in real social networks, small initial activations are enough. We don't need too much actors to spread, to maximize the spread in the network. To do this, we started with some well-known optimization problems, which are the maximum influence spread problem and the least cost influence problem. Both, the first one says that given a k as a number of nodes in this, which is the seed size, how I can find a seed of this size that maximizes the influence spread. And the other problem is given a number of nodes that I want to spread, okay, I want to convince, minimizes the seed size that can convince all of these seed actors. Both are NP-hard problems, so there is no an exact solution. There is a lot of approximation algorithms to try to solve this problem. So the solutions include greedy algorithms, heuristics, meta-heuristics, common-based algorithms, etc. And the most the best solutions are the meta-heuristics. So in our project, we thought that these k and z variables are not really important to prove our hypothesis. We want to state a new optimization method, optimization problem that is that has two optimization functions, and the idea is maximize the seed size in order to minimize the seed size in order to maximize the influence spread and the equivalent, okay, the max mean problem. Our solution includes meta-heuristics, and in particular, B-inspired computation algorithms, the most important was the PSO, which is metaheuristic inspired on the movement of birds or fishes. And it's interesting that this is the metaheuristic that produced the best results, because it's like the behavior of people trying to follow some idea. Okay, there is a lot of people saying different things, but sometimes emerge one opinion leader that started one idea, and then a lot of them continue to follow him. Okay, so that's how this metaheuristic worked well in our social networks environment. Well, these are technical issues. It's just to say that this is an algorithm. This was the original results we obtained. We can see here we prove this also in many real social networks, and this is the behavior of the metaheuristics. We can see that the blue line represents the influence spread that is continuously growing. The red one is the seed size, and the yellow is the difference between both of them. So the idea is that it continues growing up. Okay, I don't have more time, just to say that we have two main applications. One represents the voting systems, where we can convince many voters to meet some quorum, and we have also some applications regarding communication networks in educational environments. That's it. Thank you very much.
Thank you very much. Time for question. No question?
Thank you for the presentation. How many data do you need to train your network, considering that Twitter is changing their policies to providing data to understand local networks? Do you need a lot of data? You need only a few numbers, or?
Okay, metaheuristic doesn't require a learning process. It's not machine learning, so we have just the original network. Okay, so we can apply the metaheuristic on this network. The only thing that we need to do before is fix the parameters of the metaheuristic. And that can be done using, the standard goal, but it's better to consider one small network in which we know the best solution. So we prove the metaheuristic in this small network. We prove that we can able to obtain the best solution, and then we apply the same parameter settings.
And there is base solutions for brain connectivity?
Sorry?
Brain connectivity, do you have a base solution, or it's only for social networks? Do you have an idea about
No, it depends of the, the solutions are for this optimization problem, okay? So the network can be originated for everywhere, but it could be a network representing some brain network. But we need to know the best solution in this case, and then apply the metaheuristic for any other.
Okay, thank you, Fabian. We have to stop here.
Okay. Thank you very much.
Now, last speaker in the session is Arturo Amor. Is he around? Yes, he's around. So Arturo holds a PhD in theoretical physics from the Institute of Nuclear Sciences of the National Autonomous University of Mexico. He continued his research in the same field as a postdoc at the École Polytechnique in France. He is currently a research engineer in the SODA project team of Inria in Saclay. and he's part of the documentation team of the popular machine learning library scikit-learn, where his main task is to maintain the documentation and make it more accessible to all types of users. So Arturo, the floor is yours.
Thank you. With this distance, can you hear me well? Okay, good. So thanks for the introduction, and also thanks to the organizers and the whole Inria Chile ecosystem for the opportunity of being here today to present you my work, basically. And sorry about the pixels. The joke says what I actually do is train test split. So, well, I was already presented, so I will not be redundant with that. I'm part of the Inria ecosystem, but I'm based in Saclay, in the team which is SODA, which means Society in Data. And you can find me on my social networks like this. I'm not very active on Twitter, but on GitHub, I'm surely active. And yeah, I did a PhD in physics at UNAM, mostly encouraged by the fact that I wanted to be called Dr. Amor. But there were easy ways to do that anyway. So most of you already probably know what scikit-learn, but it is the #1 machine library in the world. It's not me who claims it, it's GitHub. And also there was this Kaggle survey that positions us like at the very top. Sorry about the pixels once again. But most importantly, it's completely for free, it's open source, and is very well documented. And for us, it's quite important to be open source because it's part of our goal to be accessible to everybody and everywhere, regardless of the economic position, let's say. Okay, so this is a picture of what is machine learning, and what I want to mention here is that machine learning is a subset of artificial intelligence in this picturesque picture. And scikit-learn lives somewhere in here, but we don't really intersect with deep learning. So we actually focus on what is data processing and also construction and evolutions of models. I'm going to skip that. The most common question is, what is scikit-learn used for? For instance, back in the day, we had a partnership with Spotify, and what they did is they built a recommendation system based on our software to make like a pre-ordering for importance of what could be relevant for a given user. And then you get like a list of the, I don't know, like the 1,000 most relevant songs. And then they use more advanced algorithms to make a second ordering of pertinence on top of that. So the thing is, all the scikit-learn algorithms are supposed to be like not very heavy, easy to run, and even in a laptop. And that's why we say that we focus in basic machine learning and not that much on deep learning. So that's to mention the first application, but it's also been used like for building research engines or directed publicity, detection of spam, also price fixing, yeah. So I mentioned that one of the things that we are focused in is the validation of a model. So what we were seeing before the lunch break today is that it's quite important to actually have a measurement of how is the quality of my model. So actually in the MOOC that I'm trying to pitch today, we focus mostly in the evaluation and the good practices on how to actually determine if a model is good or not. For instance, if you come and tell me like my precision or my recall is 90% or whatever, that is not enough for me to understand if your model is better than the one you're comparing with. Because you may have like by chance a subset of of data that actually does, thank you, which it does not generalize to really unseen data. Okay, so there's a bunch of reasons why a model can have variance. Could be like depending on the model itself. We were a bit philosophical in the morning, and what we do, for instance, is use techniques like cross-validation, which allow us to see how much our model, how much of the quality of relies in the model itself, like in the parameters, the choose of the weights, basically. But also you can try to measure the variance given the samples themselves or the techniques of sampling, etc. The variance given the variables, for instance. Okay, just a brief recapitulation. We all know we have like two big families of models. We have supervised and non-supervised models. And in the MOOC, I would say that we focus mostly in supervised, which are classification and regression, and they typically are defined by data that has labels, and therefore there's some sort of human validation. But even if the MOOC focus on this side, the scikit-learn library is also very good in the whole ecosystem of both big families. Okay, so now it's demo time. I hope I can actually use the computer. Good. Let's see. So in the next minutes, I want to pitch, as I said, the two versions of the MOOC we have. Let's go to Google, and if we tap scikit-learn MOOC, MOOC stands for Multi-Online Open Course, I think. I always forget about the two O's. Anyway, as you may see, there are some options here. The first option is the GitHub pages. So this is the official scikit-learn MOOC, and it's this is the version that is open the whole year, and you can access it. And actually, if you see here, you have a link to the repo, and you can actually contribute with code if you feel like so. This is the static version in the sense that we want the MOOC to be used and reused by everyone if they are willing to, and also to be able to actively contribute. You can also have, well, you have like a search bar, and we used to have a link here for Binder, but I think it's deactivated because it usually doesn't work. But anyway, no, it's just that I need to go to a given notebook. And then here you have Binder, which means you don't really need any installation. You can run it on a cluster, but as I was saying, it may take a while, and it doesn't always run. But the idea is that it can be used, and it's meant to be used by professors or teachers or whoever wants to share our content. But going back to Google, there's also the version from FUN. FUN is France Université Numérique, and in collaboration with Inria Learning Lab, we have this version of the MOOC, which is mostly focused to students, not to professors. And this one, you can actually answer some quizzes, and in that sense, you can evaluate yourself, and you can get a badge at the end. Okay, so I will make a parenthesis here just to show also the scikit-learn gallery. So if I just say scikit-learn, sorry. Just inspire on what we have seen today, we can go to the example gallery, and for instance, I want to look for learning curve. What's command F? Learning curve. Okay. Okay, so for instance, something that is in the MOOC and you may learn is how to use visualization utils that we have, visualization tools, sorry. And that, for instance, here you have what is called the learning curve that allows people to see how your model is dependent on the number of samples. For instance, imagine that you have trained your model, but you want to be sure that if you add more samples, you will not get a lot more better. So in this sense, if you have like a costly simulation or you have like a costly experiment, you can say like, okay, if I stop here taking more data points, there will be no problem because I already achieved convergence for this given model. So this is one of the nice things that you may learn if you follow the MOOC, and also in general good practices. And I want to take the opportunity to show you a trick. In the URL, you always have a stable here, and if you change it to dev, you will get the developer version with a warning here that it says that some of the content will be released, but you have to wait for it to be fully pertinent. But what I want to show you here is that a nice new feature that was built in scikit-learn using scikit-learn, which is a recommender system. So now if you go to the bottom of the example gallery, you can see pertinent content that is related to a given example. So this was my work in the last few months. And yeah, for instance here, we've been talking about the rock curves, but what we want to encourage is to say like, you know, you don't only have one rock curve. So if you tell me, yeah, I have this rock, how you see, you're basically giving me just one point in the information. What you have to do is actually cross-validation to obtain a bunch of scores and just tell me the average and the standard deviation and some sense of confidence that will allow me to compare two models. Okay, so back to the presentation. How do I change to full screen? How do I change? Command help. Command L. Okay. Okay, you're ready. Okay. Good. Thank you. Yeah. Back to the presentation. So the elevator pitch of why to follow the MOOC is because it's completely for free. You have a free certification at the end of the MOOC. There's nothing to install, and it was created and it is maintained by the scikit-learn developers ourselves. Well, at least a set of the developers, and it's guaranteed to run on the latest version of the library. So the vision of the MOOC is to be accessible with the fewest possible exigencies. In particular, we don't require a lot of knowledge in Python. We only say like the basics of what is a class, or a for loop, these kind of things. And I mean English, that's the bottleneck for some people, but there's not a lot of things that we can do about that. But we are pitching to have subtitles for the videos because at least accents can be sometimes difficult. Okay, and we also focus in the pragmatics of machine learning, not in the mathematics of each algorithm. So we want to develop intuitions. And as I was saying, we are using a licensed CC BY because we are a bunch of hippies that we want the material to be used and reused by everybody, and even if you want to make money out of it, you can. It's completely open in the full sense of open source. Which also means, as I already mentioned, that if you feel like so, you can contribute, and the idea is to democratize knowledge. The MOOC consists of 7 modules, including one introductory module, which is very small. It also has 15 videos that were intended to make it like more friendly, more dynamic. But there's a trade-off because it's harder to maintain a video. If you want to correct it, you have to refilm it. But I think it's important to give a face to the developers of the MOOC. So that's why we have some videos. We have a bunch of notebooks that have a philosophy of hands-on. You learn by doing, and also 21 exercises that help testing a little bit the knowledge that the student has. It has a bunch of quizzes that allow for us to give you the certificate. What we actually require is 60% of completion for giving the badge. And the difference between a quiz and a wrap-up quiz is the quizzes are more conceptual, and the wrap-up quiz is actually you have to code, and we evaluate the code, well, the outcome of the code. The MOOC is quite international. For the moment, we have had 3 sessions already, like at least 1 per year, with a duration of between 2 and 3 months each, and 10,000 subscriptions per session, which is a lot. It's a huge MOOC. At the end of the day, not everybody is active, but at least I would say we have 1,000 people that are active each session. And it's people that comes from all around the world. We have 140 countries with people subscribed. And well, nowadays we have mostly presence in French-speaking countries because fun is typically popular in French-speaking countries and not everywhere in the world. So that's also why I'm trying to pitch the MOOC here in Latin America, because if you, I would really like to have like a more balanced representation of people in subscribed. So speaking of representation, we have mostly a male public, and also that's something that we would like to change to have like a more balanced subscriptions regardless of the gender. And well, at least what we have noticed is that people has at least a master's degree. Some of them have like a bachelor, like 22%, but most of our public lies in this doctor or master level. And as I was saying, we have had 3 sessions so far, and in these sessions we have monitored a little bit by using quizzes how much time do people spend, for instance, in each module. And we have something that we have been tuning to have like a more smooth experience of the MOOC. So for instance, here, if you spend a lot of time here, maybe we can simplify this module, right? And also this allows us to build equivalence. For instance, in France, they are considered as credits. So, so we can say that around 40 hours of human time are required to finish the MOOC. And also by using the students' feedback, we have identified the concepts and questions that are the hardest to answer, and we have iterated through them to make the content as pedagogical as possible in each session. And we also have a forum which allows to answer questions from the students and by the developers. So here you can see that for the whole duration of the session, we have more or less constant activity. Of course, we have like some sort of periodicity because of the day of the week. And also we have an effect of enthusiasm at the beginning, an effect of panic at the end of the session. So here, once again, sorry for the pixels, it only shows how much time we have spent, the developers, or the pedagogical team in answering questions in the forum. So that's me in the top. I spent like around 24 hours of my time answering questions in the last session. But also my colleagues are like following quite close. So yeah, that's it. Thank you in the name of the team, the teachers, and the pedagogical and technical team from Inria Learning Lab. And as a call for action, you can subscribe by using this QR code or just following on internet the steps that I did, Escalera and MOOC, and you will find it like that. The one on the left is the fun MOOC. So it's completely for free and it's open for a whole year for the 4th session. And on the right, you have a QR code for subscribing to Inria Academy, which are the formations that we give. Can be like presential or in video call. But I mean, the difference is that this one is for free, this one is a bit more expensive, but you will have probably me coming to your place and answering your questions.
Thank you, Arturo.
Thank you.
Time for questions before the break. Everybody is waiting for the break. Okay. No question? Yeah. Okay.
You mentioned, if I understood correctly, that you are abroad. You are targeting, for the time being, mostly French-speaking countries.
Yeah.
Do you have any plans how to change that? Do you have any ideas or things that you need or support that you need, even maybe at a political level, to do so?
Sure, all the support that you may give us, it's welcome, because we are doing communication in our corner. For instance, communication of the MOOC, I do it in my social network, which is reduced, and of course I don't touch a lot of people. So that's why the call for action is also, if you have colleagues and friends or follow the MOOC and you appreciate it, just recommend it and pass the voice.
Yeah, that's great. And just to complement you, I mean, in India, Chile, we have been doing a lot of communication with respect of the MOOC, but not only, also with the India Academy, and you just gave a talk on the master class on the India Academy in Chile, so it's great that we'll be able to come, and next week you will be in the summer school of the IEEE EVIC, also teaching the India Academy and the Scikit-Learn, so I think it's a great opportunity to connect also to a Spanish people guide, right?
Yeah.
So thank you.
By the way, a small comment. Thank you for the remark. Yeah, that's true. And FON has a lot of courses, and the one with the most speaking people in the FON platform is actually this one, because of my communication. But it still is not a good enough effort. We have to, we have to do better.
Thank you very, very much to all of you. Thank you, Arturo. And thank you, Adrian, for your keynote. Now we invite you to move upstairs to enjoy the coffee break. And we are going to be back here in 50 minutes. It's okay. So enjoy and make friends. really slow, so the people that is coming through the stairs walking slow have the opportunity, the unique opportunity to come and sit. Okay. Welcome back, everyone. Thank you for your punctuality, to some of you. I hope you have enjoyed the coffee break. Now we proceed to the roundtable, challenges and opportunities in the Valparaiso region, which will be moderated by Nayat Sanchez P.
So now I'm the policeman of time, right? It's my turn to be. So thank you so much for being here, for staying the whole afternoon. We're almost ending this session of the Journées Scientifiques, and it's my pleasure to moderate this panel, Challenges and Opportunities in the Valparaiso region. I mean, in Inria, we have the mission of conducting, oh, we have a pet. Welcome. In India, as you know, we have the mission of conducting a research of excellence and also transfer innovation and also to support the public policies. And in this respect, I mean, the government of Valparaiso recently, is in the process of elaboration of this regional strategy for science, technology, knowledge, and innovation, in which the universities of Valparaiso are participating and defining how they will approach the regional problems like transportation, conservation, environment, water, employment, and creative industries. So after knowing that, was for us mandatory to include in the program a slot to openly discuss with some of the colleagues and representatives of the region what can we do to better collaborate between France and Chile and between Valparaiso and Inria in digital sciences. I mean, we are a Digital Sciences Institute in collaboration with the universities to solve these problems that are part of the strategy, regional strategy of Valparaiso. So to discuss this, we have the honor to count with the presence of distinguished panelists. I want to go to the stage to Adrián Palacios, full professor of the University of Valparaiso, founder of the Interdisciplinary Center of Neurosciences of Valparaiso and the Complex System Centers, Adrián. To María José Escobar, General Director of Engagement and Partnerships, Universidad Federico Santa María. I'm Patricio Orio, full professor of University of Valparaiso and researcher at the Interdisciplinary Center of Neurosciences at Valparaiso. Thank you so much for being here. Thank you so much for taking part of this discussion. And I want to go straight to the point. As we know, I'm the policeman of time, so I will start the chronometer. We have 30 minutes, I would say, to discuss a little bit. Yeah, I think it's okay. So, Adrián, I want to start with you because besides the roles that you have a researcher, you have been vice president of research of University of Valparaiso, and currently you are advisor of the Minister of Science, right? So, what is your opinion about this regional strategy of science that has been right now you are developing here in the region of Valparaiso? Which will be the main emphasis of this strategy from your point of view? And which will be the role of the universities, the government, and the private sector between all of these, and what can we do to collaborate and to promote the collaboration to help on that?
Okay, thank you very much for this invitation. And essentially, my point of view, I mean, that with a little bit more like history on this, like you say, I mean, like a vice president of the innovation and research at the university. I also was coordinated the research council for university, and I was also in the science minister, like advisor. And I think one of the reflections that I could have, I mean, and just pointing also with this new strategy that is not yet finished. I mean, they are working on that. It's an old one, and has also been in the past in kind of the disconnection between, I mean, a strategy and what the university or the, I mean, the industry or the spin-over, I mean, all of the agents that are part of an ecosystem in the region are like not has been very connected between them. So this has been something that start to be a little bit better now, where people know that if they are not working together, nothing really happened effectively. And I think now I see a little bit more coordination between these like new innovation center in the region, the university are, some of them are collaborating more between them with big projects like Science 2030, for instance. And I think this is, I see a little bit more of one projection in the future for the next 5 or 10 years. And that is very important in the sense that you can build in the future from the present and long-term strategy. That I think this is a very good, I mean, projection. We haven't had this in the past. I say, and the only I mean things that I think is, from my point of view, very important is just to have big challenges for the regions. We were talking, I mean, I just thinking about one of the possibilities that you can face is you can take all of the axes of the new strategy that, I mean, is many things. I mean, agriculture is one, health is another, energy is another one, but also is science. I mean, science, and we have very nice potential in the region like brain science, for instance, where you can put artificial intelligence, also a lot of things close to cybersecurity can be part of the study of the health, brain science, application, and I think the region has a lot of possibility just to work together. We are not doing that effectively right now. The Inria also has been, I mean, we have met before. I'm talking about what the university are doing in terms of the transfer knowledge. I mean, they create knowledge, but they are not really transferred to the society. So all of these are like the challenges that we have. So I think I'm just working together. I mean, I think this is the only way to do things for the future. I mean, and not make the competition between institutions like the main issue, because we need, I mean, we want to face that. I mean, is that we need more students. This is something that all of the university goes now in December and January, and we don't talk each other. I mean, we are thinking how many students they're going to write to our own university, and it is every year is like that. I mean, just it's the competition between universities. But you just say, why we don't work together in association, and we think the region, like the whole, I mean, the main attraction pole for people to write to the Valparaiso region. I mean, from the north to the south of the region, we have San Antonio, and we have Papudo in the other side. I mean, this is very important to think about the region as a whole, where we can collaborate between all of the institutions, not always compete between them. I think this is something that
I think the idea is just to create an ecosystem in the region of Valparaiso,
yeah,
and to connect the dots between
each institution has its own ecosystem. Not always is visible, because say, what is your ecosystem? Is the faculties that are in the university, are the students, are the, I mean, the collaboration that you have with the private sector, is the government association, is the hospital. But once you establish that, where are your connections, this start to be your ecosystem. Then the next university close by, they have another one that are also part of the ecosystem of the region. And so long, I mean, you can just build mentally and just draw what are your connections and how you can potentiate them through common projects. You know, this is an ambition that if we don't work in that vision, I mean, global vision for the region, it's very difficult.
I think it's definitely very interesting what I have been doing with from the region of Valparaiso. Maria Jose, you as a researcher, by the way, an historic also collaborator of Inria and also Inria Chile, you have been also involved in the government as a representative of the Ministry of Science here in the region. But now you are the General Director of Engagement and Partnership at the university, right, of Federico Santa Maria. So you have been in all these roles, and how you see the opportunities, and more importantly, I mean, how the digital sciences are connected, how you think that France and Chile can be more connected with Valparaiso, and how can we make grow the ecosystem and innovation? I mean, what are you doing from the university? What are the initiatives?
I think that thank you for the invitation for being here. I think the first thing we learn is that we cannot work as an island. We have to work collaborative within all the actors that pushing forward. What we call is it's not just ecosystem, it's as innovation-driven entrepreneurship ecosystem. So we have as a university region, we have a big capacity of creating innovations, but we have a very low capacity to transfer this innovation to the private sector or to the public sector. So I think we have to work collaboratively. We have to change the mindset of how to do that. And in order to change that mindset, we have been trying different ways, different manners to create this transfer. The first thing is that we created in the university a deep tech innovation district. So it's trying to connect all the alumni, which is working mostly in the private sector, with the students and the researchers in order to increase the number of spin-offs created by the university. The other different activity is that if we want to create a spin-off, it's not only our students or our researchers who's going to be part of this spin-off. We want that the spin-off also have the participation of people coming from the private sector. So we are talking all together. So for different innovation that we have identified, we are directly talking with the people from the private sector who is interested in to participate in this company, new company, and trying to understand what is missing, which are the mechanisms inside the university we have to create in order to promote this collaboration. So it's not only spin-offs coming out from the university, are spin-offs that are formed by people from the university and people from the private sector at the same time. And in order to the challenge, in the region we have a very strong community of people doing research, scientific research, and also we have a big community of people developing technology. And they're not talking between them. So we have to transfer, or we have to make this, how this technology will help the scientific community to do better insights, and how the scientific knowledge could improve or could give orientations to the technology we are developing. And in this direction, how this region, we have a very diverse economy, we have many sectors. So this technology can be applied to many challenges that we have, like water management, like food technology, like earth technology, video games, creative industry. So there are many industry sectors where the technology and the science can be combined to create value.
Yeah, it's amazing what can be done. I will come back to you through your last comment, but before that, Patricio, you're a researcher, right, of the Interdisciplinary Center of Valparaiso, and also a director of the PhD program of neuroscience, biophysics, okay. And by the way, Patricio and I were last week, part of the panel Tertulias Porteñas, discussing a little bit in a more physiological way how neurosciences and AI connected. I mean, both ways, and I mean, in the inspiration side and the application side, right? So from the work you are doing in the Interdisciplinary Center of Neurosciences in Valparaiso, I mean, what do you think we can better exploit, connect what is done in France and what is done at Inria as a research institute in digital sciences, and what are the challenges from your field that you think we can use, exploit, and better connect, and what are the opportunities that you see in this respect?
Well, as Adrian said, there is a strong community, and now I would say a tradition in the region in neuroscience, also in biophysics. And since many years, it has started to mutate or to direct to this interdisciplinary approach where we can apply computational science, mathematics, engineering to start solving new things. This is the spirit of the PhD program that I am the director right now, a PhD in biophysics and computational biology, with the intention of attracting students from mathematics or engineering and teach them some biology, and attract a student from biochemistry or biology and teach them the mathematics and informatics to do something different. And I have seen also in the University of Valparaiso, I saw the birth of this another program, PhD in science and engineering for health. And from a little distant place, I also saw the birth of the applied informatics PhD program. And all of them share this vision of hey, we need to get these two worlds together of things that we can do right now, mostly in health. That's what I have seen more, but I think there are other fields that it can apply. And there is a lot of interest from the students to do something, to feel that they are just doing something useful with mathematics, with informatics, with computer sciences into these fields. So we are generating this kind of ecosystem. And now, as we are detecting that it's kind of so far a little bit isolated, not so much from other institutions. Here, the Universidad of Santa Maria, there are some links. I also participate in a research center here, but still we need a little bit more some effort. Maybe Fabian that was talking about this social network maybe could give us some advice on how to foster these networks and make this a little bit more united and create a really not only one ecosystem in Santa Maria, another ecosystem in Valparaiso, another in the Católica de Valparaíso, but also instead a real regional ecosystem. I think that the raw material is there. I mean, there is material to work with and to create a really interesting regional ecosystem about that in this interdisciplinary graduate education that can really bring or attract brilliant students to solve these interdisciplinary problems.
Yeah, this is great. I mean, and yeah, there's a lot of things that you talk now here, but and I want to come back to Adrian, the ones that you mentioned. I mean, because we know that historically has been a disconnection between the research that is being done, I mean, in the high-level labs and that is conducted inside universities from the real problems and with respect to the impact of this research, okay, beyond the papers, right? So, and then always tough to motivate researchers to think out of the box and do this extra mile to connect, right? To connect in different aspects of society in general, right? And we have been discussing here about talent education, about the role, I mean, of a strategy in general, and there are some initiatives in innovation, entrepreneurship as a very particular actions inside the university. But what do you think that would be, I mean, what will motivate? I mean, what will motivate? What needs to be inside this strategy that you are building now to motivate really the researchers to get out of the box and do and think of the impact from the regional point of view?
Yeah, what you say, I mean, is what you ask for. I mean, opinion is like the center of the big change, because I mean, you need to change a model. The way that we are working today is, or has been for the last 20 years actually, is more like each institution look at their own survival, in the jungle, something like that. And today I think people have been realizing that for more that you are working hard, you still being in the same position, and the country is still in the same position. I mean, it's something that is very global, but what happened in the other countries, in South America, is not very different from the last 20 years. So we're still having undeveloped countries, with a lot of division internally. And if you change that, you say, okay, what we don't start something more radically we just build a model where we need collaborate. We need collaboration, we need integration, and we are thinking more like an regional development, and you start to collaborate with the big challenges that we need to. It's an option, political option, like the what Mariana Mazzucato is saying about mission, but actually I realized that I reading few weeks ago that France has a very nice project today that is based in challenges where the regions, and different partners associate to solve a problem. And this problem, when the association between different agents is done, you make a proposal and then you can get funding for the government for the big challenges. So that make union, for a big goals. And this kind of the change need to come from a government in general, all the regions, and then everyone can work together. I mean, together, university, enterprises, public, private.
Are these big challenges already defined as a region?
They are one,
clear?
but the way that I saw this program that is in France is already working. I mean, they create this
in the region, in Valparaiso.
we have. I mean, the strategy gonna have the past one was having some challenges, but were never implemented like a program. That okay, we need to solve. We have a time to do that, and we have also the funding. That has not been happened yet. I mean, in this scale, no.
But it's true. It's true that the global challenges and the big challenges are something that connect us very well. We saw that in the pandemic. We work like that, and probably there's a lot of know-how, for example, from friends, and also as an institution at Inria. I mean, we have like a program inside Inria, which is called Inria Challenges, where the main objective is to connect the dots, to connect the Inria teams, the 220 Inria teams that we have, to solve like a big problem. Okay, so that's more or less the same idea, but at an institutional level, right? So the idea is that probably you conduct something like that at the regional level, and then in the level of the universities too. So what is the role, Maria Jose, with respect to the universities? What are you approaching this? Do you have in the university, I mean, it's the University Technical of Federico Santa Maria, right? So what are the particular challenges, sectoral, I don't know, how is the university organized in this respect? There are some specific topics, applied topics that you...
There are global challenges that we cannot avoid, like SDGs and all that, of course, they're only present.
We all agree on that?
Yeah. In the region, we have water management. We live in a country where we have a lot of natural disasters. There is all about misinformation, disinformation challenge that are also locally applied that we can address that. And also, and we are, as innovation entrepreneurship ecosystem, we are also organizing different meetings where the people coming from a certain type of industry is proposing which are the challenges. Which are the challenge of the agri-tech industry? Which are the challenge of the logistic industry? What are the challenge of the mining industry? And once these challenges are explained, all in front of different researchers, startups, etc., we are trying to make matches of which kind of people could be working or knowing more, get deeper into those challenges and trying to understand and make connections. But I think it's not only challenge, we also have many opportunities in the region. One of the opportunities that after Santiago, we concentrate the highest number of graduate students. Okay? And after Santiago, we also concentrate the highest number of deep tech in companies, small companies. And these are opportunities that cannot be avoided. And the third one is we have the Navy here. And we know from Mazzucato and all that if you put big challenges, normally driven by the defense industry, that's at the mission-oriented innovation, could highly impact the local economy and the development of the universities, technical research center, etc. And I think this is a very great connection of what Inria is doing on all these startup studio program that you have. And there is a lot of knowledge we can exchange and learn from your experience in order to better take advantage of the local opportunities we have here.
Yeah, great. And how is your vision with respect to that, Patricio? I mean, from your researcher point of view, what do you think and your PhD? I mean, because talent also. How do you connect internationally this PhD program? Is that a thing for you? How do you connect it with the local?
Sure. Yeah, I mean, we have actually as a in particular, in very concrete, we have as a program, as a PhD program, we have this challenge for the near future of increase our connections with both national and international institutions to have more, how you say it, is vinculación, I don't know, more links to other institutions. So yeah, we have thought a lot about that. And in the case of graduate education, PhD programs, it's kind of easy because most of us as researchers have some collaborations international, and it's kind of easy to send, well, as long as you have some access to some funding, it's kind of easy and very useful to send your students to, and also to receive students from others. And this is something that has happened a lot with the collaboration we already have had with Inria and other institutions also. There are many funding opportunities to establish that. So maybe we can, perhaps it's a challenge to make some other, to spread the word a little bit, and some other researchers that maybe are not so aware of these opportunities that can really foster a good collaboration with Inria or other institutions, and that could be a good way. And I forgot, but yeah, and then we need to also maybe, because when you said this program in Inria that trying to connect the dots to make the many 200-something teams to work on something big, yeah, that's kind of easy because that's one institution. But here we have different institutions. There is no one big head that can make an order to do something. So maybe it would be interesting.
From your researcher point of view, what will motivate you to be involved in such initiatives? What is the main incentive?
Yeah, the main incentive. Well, there are kind of good and bad incentives, and sometimes the most visible are the bad ones, which is the money. So okay, if you want some money, you have to disguise your project as something applied. This is something that it's happening a lot. So, but yeah, now some researchers are making the real mental change of doing actual applied research, which is good. I see also the danger there of leaving or starting to not funding enough the basic research, which has to be funding also. So it's this kind of a balance that is hard to manage, but I see it as a potential danger. But yeah, so the idea is that the incentive is when you notice and you see that your research is being applied, is also attracting good students, because if they see something very useful, attractive, or I don't know, an application in the health or in the industry, you are also going to attract the better students. So I think that those are the incentives, and they are slowly but steadily gaining a little bit of strength right now.
Right. A final word. I mean, we have 5 minutes. Can we say like a tweet? I mean, each of you a tweet of that could connect, I mean, the dots between the region of Valparaiso and France and Inria and digital sciences?
In terms of the challenge or the future? I mean,
in terms of whatever you want. How would you connect it?
Yeah, there are the two issues. One is culture. I mean, we are also thinking the North-South collaboration, but sometimes it's very asymmetrical. So in that sense, the idea just to build capacity in the region, I mean, South, is very important also in dialogue with the other partners. I think this is a big issue that now is people are more liking to come here, to stay here. This is something like create a landscape that everyone is more comfortable there. It's not just to explore brain, but also to capture capacity and install capacity and develop your own way to do science and just thinking in a better society. And that we can collaborate with real like partners, you know. This is a big issue that is nice to think about.
Okay, building capacity. Maria Jose?
Yes, we have built capacity, and also we have challenges where we have to digitalize process, get data, manage that data, and optimize many of the local industry with that data. That's a very straightforward collaboration with what Inria is doing. And also to connect and how all this sort of research, there's a long-term research of the region in mathematics, neuroscience, and optical network, etc., how to make this research being connected with the economical development, sustainable economical development in the region.
Patricia?
Yeah, I think, well, as we said, that there is material to work with here a lot. I mean, there are researchers and students that are really willing to make this connection with the things that Inria does. Maybe what is missing is I don't know, somebody from social network sciences or something like that to kind of to tell us, okay, so you have to put your efforts there. I don't know, in communication, or maybe more funding here and there. Maybe it's small things that could catalyze this bonding and efforts. Because I mean, it's happening. I mean, it's growing, the number of collaborations, the interest of the persons, but it could be faster. And I think that maybe think about it, not think aside of the science or the applications. Think a little bit on how the interpersonal or interinstitutional relationships can work better. Maybe that could help. I think that's maybe something that could be thought about.
Yeah, absolutely. Thank you so much for being here, for the brief discussion and connecting to the next session that we will be presenting the programs. What? Oh yeah, for sure. Okay, you have questions. Okay. Before connected to the next session. The know-how that we can.
Yeah, it's possible that this is one. Yeah.
Great, and now more questions? You need that.
You can shout.
Well, it's not really a question. It's just to announce an opportunity of collaboration here in the region of Valparaiso. We are running, I'm from Catholic University here in Valparaiso, and we are running a brand new program, master program, on scientific computing, okay? So the idea of this program, the students, in order to graduate, they had to develop a simulation outside from the walls of our institute, which means we can send students to collaborate with Adrian or with Inria or companies or whatever, okay? So the final work of these students, they have to develop a simulation which is co-supervised between one professor of our university or our institute and a professional or another professor from somewhere else outside the walls of our institute. Okay, so I think this is a great opportunity of collaboration inside the region, and thank you for listening.
Thank you so much again for being here in this opportunity. You want to say something? Go ahead.
No, I just wanted to say thank you for the information. That's amazing opportunity for many of our researchers also. I think we should get in contact soon.
Absolutely. And now we connect to the next session. We will be presented the opportunities of the cooperation programs between Inria, and also to say a few words about the Inria network for French-Chilean Inria French-Chilean network of researchers, right? I do it right. Okay. And then the cooperation programs that can allow us to cooperate, Patricio, also in basic science, not only in applied. Okay? Thank you.
Yes. Thank you, Najat. As you said, now we welcome Cecile. And yeah. So yeah, undoubtedly the Valparaiso region faces very interesting challenges. So, and now we welcome Cécile Bigorou and Claire Saint-Léger from the Direction of International Relations at Inria. Oh, and also Luis Martí, our scientific director.
So I will be very brief because I will leave the floor both to Claire and Luis to give a few words about the two main focus we want to do. First of all, we want to underline the importance of the scientific collaboration for more than 10 years now between France and Chile through Inria Chile, and all these fruitful collaborations have led to a network of more than 650 collaborators already working or have been working together, and the idea is really to capitalize on this already existing ongoing collaboration, or were in very recent past, but maybe are on hold for the time being, and to have a dynamic network of French and Chilean researchers. And we are really, really eager to have your input and your feedback about what was mentioned a little bit in the previous session. What do you need? What do you want? And what will be your plans to develop the collaboration? And we will give you in a few minutes examples of the tools that are already existing, especially at Inria level, to encourage and to support this collaboration. But we, as you will see, we have quite a few programs that are, I would say, Inria homemade. So we can create new ones. We can create new ones together with Inria Chile, definitely specifically targeted toward this collaboration. So I will leave the floor to my esteemed colleagues that will give you more information, but do not hesitate to contact them for more questions and to develop the collaboration. Thank you. Sorry, and one last point, because I will forget it tomorrow, and I really want to thank all the researchers that are here present, and especially the ones that are in the room that came from France, from different cities in France. So do not hesitate to discuss with them, because this is really to be able to meet in real life and not by video conference is really a very good opportunity to exchange. So I guess we may have a few minutes also afterwards to discuss with them. Thank you.
Good morning to everyone. Voy a presentar en español hoy para cambiar un poco para mí los indicadores de Francia que ya habían escuchado la presentación. Pues nuestra red Inria franco-chilena de investigadores fue anunciado oficialmente en 2022 durante la primera edición de los encuentros científicos que tuvieron lugar online para la primera edición. Y pues son actividades que ya existieron, pero el objetivo era fortalecer el papel de Inria Chile para dos objetivos. El primero es apoyar las colaboraciones que ya existen entre Inria y los equipos Inria y los equipos de las universidades chilenas. Y el segundo objetivo es fomentar nuevas colaboraciones. Y por eso, en conjunto con nuestro Departamento de Relaciones Internacionales en París y el equipo detrás de Nayati Luis, todo el equipo de Inria Chile, identificamos las oportunidades en Chile y en Francia que pueden interesar a los dos, también los tópicos de interés mutuo, y les ayudamos a encontrar nuevos socios como institutos de universidades, como talentos doctorados, postdoctorados o estudiantes. Y Inria Chile organiza también eventos científicos para actividades de networking, para que los equipos se encuentran. Y compartimos todas las informaciones sobre las oportunidades, los eventos, los proyectos y los programas que apoyan las colaboraciones de diferentes maneras, individualmente a los investigadores identificados y también a través del sitio web de Inria Chile y de las redes sociales de Inria Chile. Concretamente, pues hay estos eventos como los encuentros científicos hoy, Summer School y otros workshops. Y hoy quisiéramos enfocar la presentación en los programas que existen para apoyar los proyectos y la movilidad. Tenemos un exitoso programa de Inria que se llama Equipos Asociados, que apoyan proyectos entre un equipo Inria y equipos extranjeros para un periodo de 3 años, y hay una llamada anual con una fecha límite en octubre, que estará publicada para la próxima, en junio o inicio del mes de julio, y financia visitas y workshops. En Chile tiene un éxito desde mucho tiempo, y desde la creación de Inria Chile había 30 equipos asociados y ahora 8 equipos asociados activos.
Okay, so we have other programs. This is lo siento. Ya no sé en qué idioma hablo. Menos francés, cualquiera. Bueno, tenemos este otro programa de los Inria International Chairs. Es un programa para atraer investigadores del mundo a Inria. Hay 2 categorías. La primera, que era la digamos, habitual hasta ahora, que era para atraer investigadores en una etapa más avanzada de la carrera. Y ahora hemos creado dentro de Inria esta otra categoría, Starting Career, para jóvenes investigadores. La llamada es, bueno, como ven ahí, en octubre de cada año. Y bueno, si están interesados en aplicar, no duden o sea, cualquier investigador externo a Inria puede aplicar a esto. Después tenemos estos postdoctorados que están, digamos, financiados por la Dirección de Relaciones Internacionales. Digamos, para trabajar en un tema relacionado y asociado con Chile. Ahora mismo, de hecho, tenemos a Katia por aquí, que está dentro de ese programa. Katia debe estar haciendo sus slides de mañana, que no me las ha enviado. Bueno, es otra oportunidad para, digamos, abonar esta colaboración. Y por otro lado, tenemos este programa de pasantías en que cada año 5 estudiantes de 3 universidades chilenas, entre ellas la Federico Santa María, se pasan una pasantía dentro de un grupo de investigación de Inria en Francia. Y es un programa que tengo que confesarles que, bueno, creo que todo el mundo está muy contento. Nosotros en Inria Chile, los investigadores en Francia también. Tenemos varios casos, incluso en las jornadas científicas hemos ya visto alumnos que han ido a hacer una pasantía en Inria, han vuelto a Chile, ahora están haciendo un doctorado en Inria. Entonces se crean estas sinergias, y yo, o sea, si fuese alumno, intentaría anotarme para la siguiente llamada, y si fuese profesor o académico, intentaría que mis alumnos se anotasen, porque lo que está sucediendo, y lo hemos comprobado en varios casos, es que a través de este alumno se empieza a crear una conexión, una red, que después entonces podemos reforzar con un equipo asociado y ir progresivamente adicionando recursos y haciendo crecer estas oportunidades. Después tenemos otros programas que ya no son locales a Inria, pero de los cuales nos podemos beneficiar, como son los ECOS, los programas ECOS, que está financiado por el Ministerio Francés de Relaciones Exteriores y la NIT. Seguramente todos los conocen. Hay un programa similar, que son los programas ANSUD, que están agrupados en 3 temas, uno relacionado con el clima, otro con matemáticas y otro con las tecnologías de la información. De nuevo son para financiar proyectos, en este caso de 2 años, y en este caso resulta muy interesante porque hay que envolver al menos 2 países de Latinoamérica. Entonces también permite, y de hecho hemos tenido varios proyectos de este tipo, permite crear redes no solo con Francia, sino también con Latinoamérica, conectando con la conversación de anteriores. Es bueno también tener esta conexión, digamos, local más o menos, porque Latinoamérica es muy grande físicamente. Entonces, sé que he hablado un poco en Fast Forward, pero por favor cuenten con nosotros, tanto con el equipo aquí en Chile como el equipo en Francia. Cualquier duda que tengan, incluso si no, o sea, les podemos ayudar. Yo siempre digo que tengo como 2 gorros. Una parte es el trabajo de investigación que hacemos en Inria, Chile, y por otra parte la investigación que conseguimos articular y conectar con la gente en Francia, ¿no? Pues nada, muchas gracias, y si tienen dudas o no duden en preguntar. ¿Está bien?
I don't trust my memory. I know that I have the sad mission of let you go. But I want to tell the right words for this day that has been amazing. I mean, being here, I guess for all of you, but also for us as a team, in this wonderful city. I'm out of the script. I just wanted to let you know that has been really, really great to share with all of you today here. So thank you very, very much to Cecile, Claire, and Luis for letting us know about all these wonderful opportunities. Also, thank you very much to all the panelists, to the authorities, and to all the participants who brought life to these 3rd days of the Journées. We remind you that tomorrow we will meet again, starting at 9 a.m. at the auditorium of Vice-Rector Office for Research and Development, Emprende UC, University District, en la Universidad de Concepción, where we will have the last and exciting days of the Journées, filled with essential scientific conversations. See you tomorrow. Thank you very much and have a good evening.